Okay, so Triple and I here, and I have something that's vaguely related to electronics today. It's been 7 months since I did anything serious, at least in terms of an investigation or um, looking stuff up or coming across interesting things. Basically, just experimenting. So, what we have today here is a Raspberry Pi Pico, as always. And the rumbling in the background is just a train, by the way. So I have a makeshift probe spring clip made of a piece of lead-free solder because that's all I have right now, and that's feeding into this my HP 54600A, which is a 100 megahertz two-channel scope, and there should probably be an asterisk near this 100 megahertz and maybe some fine text on the back, which is what we are going to be investigating today. So, as you can clearly see, there's a bunch of pulses on the screen. The pulses don't look very square, which is unexpected for a Raspberry Pi Pico at 2 milliseconds per division. And there does not seem to be any reasonable way of triggering this signal. If I go out of range, it just holds still for an instant and then starts going crazy again. But you can kind of get an idea of what the pulse looks like. Well, the truth is, these pulses are not 2 milliseconds, or, well, to be more precise, 1 millisecond long. If you zoom in more, you actually see that the pulses the Pi Pico is putting out are approximately, well, this is not a square pulse, so I don't know how wide I should call it. Let's say 5 nanoseconds long. And what we are seeing here at 2 milliseconds per division is aliasing, very bad aliasing. Of course, this is a really old scope, so I guess that was to be expected. Okay, it's kind of triggering. Never mind. Okay, so this is basically converting a really high frequency signal into a much lower frequency that is not actually there by sampling at a multiple of the input frequency. So what the scope ends up seeing is 1 point on this part of on this pulse, 1 point on this pulse, another point on this pulse, and eventually at a certain time base it kind of ends up recreating the shape of each individual pulse approximately by averaging a bunch of pulses. It's not exactly averaging, but rather sampling a different point on each pulse. And because each one of these pulses is more or less identical, you get to recreate a fast pulse on a much slower time base. So, this has implications, and the biggest one of them being you can digitize a really fast signal and a repetitive one, a fast repetitive signal at a frequency that's slightly less than an integer multiple of that frequency, slightly more or less, I'm not sure. And you can technically recreate that signal on a much slower time base. And that is exactly how sampling oscilloscopes work. This oscilloscope is a sampling oscilloscope, which is, uh, if you can see, each of these samples happens randomly and it's all recreated to form these pulses. I wish I had a better example of a waveform to show you this effect. Maybe I can quickly change the code on the Raspberry Pi Pico since it's running Python after all. Right. Okay. So let me greatly increase the duty cycle of this pulse. So each pulse happens, decrease the duty cycle, not increase, so that each pulse happens less often. And that can be accomplished in PIO using a bunch of no-op statements. So I've added an arbitrary number of no-ops. Okay. PIO ASM error delay too large. Aha. There should be 31 delays, not 32. Let's see. Maybe some more delays. Right, so if I move the time base around, okay, the effect is slightly more visible. You can see that if I move this waveform around, a part of it stays in place, and those dots, those samples are not really uniform, so this is random sampling. Very low duty cycle. I could probably take it down even more, but I couldn't be bothered. So, you could consider this a proof of concept for a sampling oscilloscope. I am planning to build one eventually to be able to digitize gigahertz level signals using a diode bridge and stuff. You don't really need much more than a diode bridge and something to drive it at a certain frequency, and I think a pi pico could do that easily. Supposing you focus. Supposing you sample at something like 200 megahertz or something, it should probably be possible to digitize gigahertz level repetitive signals. So yeah, an old oscilloscope, but a really interesting one.